All right, here we go. This is problem number 61 from chapter 5 of the Halliday and Resnick physics book. So the idea is we've got this balloon. So here's our balloon. Passenger, hello. So the balloon has a mass of capital M, and it's descending downward with an acceleration of a. I'm going to go ahead and make that negative to indicate the downward direction. All right, and so then the question is, if we're going to throw mass out of this thing, the question is how much mass, lowercase m, do we need to throw out to give the balloon an acceleration upwards of positive a. Okay? So that's kind of the idea there. Oops, I don't know why I just did that. So let's take a look. So in the first case, before we've reduced the mass, there are two forces acting on this thing. Gravity is pulling it down with a force equal to the magnitude of the mass. Well, I said magnitude there. It's equal to the mass times the acceleration of gravity, right? And then, if that was the only force, then we would have a problem because our balloon would be falling, it'd be in free fall. So there's this other force, lift, that is decreasing that acceleration. Okay? And so the idea here is we can write an equation that relates the forces in the drawing to this acceleration. Specifically, we know that net force is equal to the mass of the balloon times the acceleration of the balloon. Let's make it negative there just to indicate that the net force is going to be negative there. So we're assuming A here to be a positive number. Okay? Now, we also know our net force is the total of all forces, right? So for us, that's the force of the lift minus that force of gravity, right? All right, so there's one equation. Now, our goal is, over here, we want to end up with kind of the same idea, but we want to end up with a positive acceleration. So again, let's see if we can figure out what forces are on it. Well, our force of gravity is still here, but it's going to be a smaller force of gravity, right? Because we've got less mass, therefore less weight. All right? But the problem says assume that the force of lift hasn't changed significantly. The idea, well, never mind, we haven't learned about lift yet. The idea is that the balloon still sort of has the same volume, so it's going to displace the same amount of air. So it's going to have more or less the same lift force. All right? So let's kind of go through this process again. So now we've got that net force equals m minus m times a. Notice positive this time. And so that gives us this equation. If we replace net force, so write it down here where I have a little bit more room, we're going to have the force of lift minus Okay, so there's our equation. All right, so the idea is we've got these two equations. We got this guy, and we got this guy. And our goal is we need to come up with an expression for m, right? For lowercase m. When you're given a problem like this, though, really the only sort of legal variables that we can do this in terms of are the variables that are given to us, right? Like, ordinarily, we'd be given a problem with numbers, and this capital M here would be a number, right? And we'd be given this acceleration, right? And so our answer needs to be written in terms of those values. Yes, it sort of references the lift, but it doesn't tell us sort of what that lift is, okay? So our answer needs to be in terms of those variables, and then any other constants we know. And you can see here that the answer is given. You can see that it uses g, and obviously we know that g is 9.8 meters per second squared. All right, so those are sort of the things that we have to work with. All right, so let's free up some space here, and basically from here it's just going to be some algebra. All right, so there's a couple of ways you can do this. Option one would be to take both of these equations and solve them for FL, the lift force, and then set them equal to each other. And you know what? Well, let's just do it that way. It's not really good on paper, but that's probably just as easy as anything. The other option would be you've got two equations here. If you subtract one equation from the other, then your lift forces cancel out. Okay? So, but let's do it the way I said first. Let's solve them both for lift. So this first equation, if we solve it for lift, becomes lift force equals, I'm going to add mg to both sides. And so you get capital Mg minus capital Ma. The bottom equation becomes lift force equals, I'm going to add this mess to both sides. So I'm going to get M minus M times G plus M minus M times A. Cool, so now I'm just going to set these two things equal to each other. And our goal is we want to solve for lowercase m. So I'm looking at this. Mg minus Ma. I've not given myself enough room. Is going to equal M minus Mg plus M minus Ma. All right, let's see. If we solve this thing, well, I got to get rid of these parentheses over here, right? So the left side I'm just going to leave as Mg minus Ma. Over here, I'm going to have Mg minus Mg plus Ma minus Ma. All right, so here is what I notice. Oops. Sorry about that. Okay, so the mg's are going to cancel on both sides, right? If I subtract mg from both sides, these guys go away. Let's see. I want to get my m's by themselves. So let's move this guy here to the other side. So I'm going to have negative ma minus ma equals negative mg minus ma. All right, so there's my equation. So we can multiply through by a negative and make everything positive. That simplifies things. So here I've got ma plus ma. That's just 2ma equals, over here I've got mg plus ma. Oh, I can factor out an m. So we get 2ma equals m times g plus a. Aha! And now divide both sides by g plus a. So you get m equals 2 capital Ma over g plus a, which matches the answer on the sheet there. All right, so there you go. Algebra.